So in question 8, we're going to do a bit of graphing of some constraints. So there are three inequalities here, right, with two variables. Y is greater than negative 1/2 x plus 7. Y is less than or equal to 1/3 x plus 3. And y is greater than x minus 5. We're going to graph those and we're going to shade the solution region. The other thing that this problem asks for is for us to give, and let me highlight this so I don't forget it. It says give three solutions to the system that have integer values for both x and y. So what we're looking for are points like, for example, x is 2 and x is 5. Those are both integers. And if 2, 5 is in the shaded region, that could be one of the points that we write down. So I've got some graph paper. This was on your test also. It was already set up. Let me just sketch this over here. Let's look at the first one. The first one has a y-intercept at 7. So I'm going to come way up here at 7, and I'm going to sketch a dot right there. And it has a slope of negative 1/2, which means I'm going to go down 1 and over 2, and down 1 and over 2, and down 1 and over 2, etc. Now, unfortunately, it has to be greater than that line, so I can't grab my line tool at this point and just go for it, because that would be solid. And I don't know, actually, in OneNote, I haven't figured out how to put dashed lines yet. I haven't looked very hard, though. But I'm okay, I'm done with that. So this is, my boundary line here is dashed, so because it says it's greater than, it doesn't include these points. So I'm sketching a dashed boundary line. There we go. And now what we're saying is that my y values are those things that are above this boundary line. So I'm going to be shading above this particular line. And I'm going to leave that in red. So above the red dash line is my first boundary. Let's go to another color pencil. So the next one is y's are less than or equal to 1/3 x plus 3. So here's my y-intercept at 3. It's nice that these are all in slope-intercept form already. And I'm just going to go up 1 and over 3 units, and then up 1 and over 3 units, up 1 and over 3 units. And this does get to be a, let's see, this gets to be a solid line, right? So I can go ahead and grab my line tool. Where are you? There you are. And I'm just going to go ahead and graph this line. Oh, now wouldn't you know it, the line is red. Let's see if I can change that. No. I can change that, but for some reason I feel like it's going to be more work than it's worth. Change you to, you're supposed to be a green line. Oh, now I've got different choices of green. This is ridiculous. Okay, there we go. And it says y's are less than or equal to that. So I've got the or equal to, so that's the solid line, but less than this curve are going to be those things that are below that. So I'm going to shade below the green curve and above the red curve. So I can kind of see, I'll have to erase this, but already there's kind of a solution in here, right, that meets those. But there's one final constraint, and that is that y's are greater than x minus 5. Now, in that particular equation, right, the slope is 1 because it's just 1x, so up 1 over 1. And I've got a y-intercept at negative 5. So for this one, let's bring in a blue pen, and I'm going to go all the way down to negative 5. There we go. And I'm just going to go up 1 over 1, up 1 over 1, up 1. And that's pretty easy to see what's going on, right? Although, I don't know, my eyes just lost it there. So I think I can go ahead and just draw this dash line, right? Just going right through these points like this. My gosh, I think I'm getting cross-eyed. Okay, and finally it says that the y's are greater than that, not greater than or equal to. That's why it's supposed to be a dash line, but greater than that. So here's what I've got. My solution region is right in here. I'm looking at this spot that I'm trying to shade in yellow, right? Now, that's fabulous, and we're almost done. The final part, it says, remember, and I highlighted this, give 3 solutions to this system that have integer values for both x and y. So if I zoom in a whole bunch here, right, I can see I've got, for example, this point, this point, this point, this point, this point, and you know what? If it can be that, I guess this point works too. In fact, that point would work because it can equal that. This point, and that looks like it. So there's only a total of 1, 2, 3, 4, 5, 6, 7, 8. Unless I'm missing something, it looks like there's only 8 points that are possible. Down here, I can't, although I think the blue is supposed to go right through there, I can't include that point because it was, those were dashed lines. Same reason why I can't include that, because these were dashed lines. So anything on the red or blue lines can't be included, but the ones on the green line can. So this is a solution and this is a solution. So it doesn't really matter which of those points you pick, just as long as you pick 3 of them. And just to finish, I'm going to go ahead and say that my 3 values are, oh my gosh, can I read them? 8, 4 is 1 point. Another point looks like 8, 5 also. Let's see, we've also got a point at 9, we'll say 9, 5, and we'll just stop there. So there are more points that are solutions. By the way, we are saying, remember, we're saying that any of these points that are in that solution region would make not 1, not 2, but all three of these would be true simultaneously. So this is absolutely an amazing thing. Those 3 points are all systems. It's a system. They're solutions to the system, but they also make the individual constraints true. Okay, that's it for this question.